All right, good morning or good afternoon. We're going to start today with lesson 5 of module 6. We're continuing with the same objective from yesterday, so we will be describing graphs that we see based on real world situations, basically. You'll know you're successful when you can sketch the graph that exhibits the qualitative features of a function based on a verbal description, and that's just fancy language for you'll know you're successful when you can read a verbal description and understand the graph that pairs with it and why it does what it does in terms of increasing and decreasing and remaining constant. Okay, let's go ahead and get started. All right, starting with example 1. So it starts off actually on this side. I just put the words over here, and it says, not all real-world situations can be modeled by a linear function. There are times when a nonlinear function is needed to describe the relationship between two types of quantities. Compare these two scenarios. So the two scenarios are on the left, and they're shown in verbal descriptions and in graphs. So the first one says, Aleph is running at a constant rate on flat paved road. The graph below represents the total distance he covers with respect to time. So you can see that as time goes on, he covers more distance, right? It's increasing at a constant rate. It means he's pretty much running at the same speed, and the reason being, well, he's on a flat road, right? Now, if we look down below, it says Shannon is running on a flat, rocky trail that eventually rises up a steep mountain. And the graph shows her distance over time. So as time passes, this is how her distance increases. So she starts off flat, right? She's going pretty fast. But then it's a rocky trail, and eventually it rises up a steep mountain. So you can see that her speed, she slows down, she covers less distance, and it kind of curves off. Okay? And that's because that's what her situation has her doing. So let's look at these a little bit more in depth by answering these questions over here. It says, for number 1, in your own words, describe what's happening as Aleph is running during the following intervals of time. So from 0 to 15 minutes. So from here to here, what's happening right there? Well, within that 15 minutes, he is going 2 miles. He runs 2 miles. Okay? It looks like it's a constant speed. He's not increasing or decreasing faster at any point in time. It's just constantly increasing at this rate. Okay? And then it says, describe 15 to 30 minutes. So from there to there. Well, within the next 15 minutes, he runs a total of 4 miles. So he runs another 2 miles. Okay, 30 to 45 minutes. So 45 is right here. So this chunk of time, well, you could probably see there, this line matches up here. He runs a total of 6 minutes, so he runs another 2 miles. And you can probably guess the last question too. Okay, you can see that he is increasing at the same rate. Every 15 minutes, he runs 2 miles. That is his constant rate of proportionality. And if we did y divided by x, if we did distance 2 divided by 15, we would get our constant of proportionality, or our slope, our rate of change. Okay? Now let's look at this one below that represents Shannon. It says, in your own words, describe what's happening as she runs during the following intervals of time. So from 0 to 15 minutes. Let's look at her graph. So that's this section right here. So within that 15 minutes, she ran, it looks like 1.5 miles. That's where it lines up right here. So in the first 15 minutes, she ran 1.5 miles. 15 to 30 minutes. So that lines up probably a little bit over 2. Okay. And the next 15 minutes, she ran, well, looks like maybe right there. So let's say like a little over 2 miles. What do you think happened during this period of time right here? During this next 15 minutes? Well, I would say she definitely hit that mountain, right? It became steep as she started running up this mountain. Okay. The next chunk of time, to 45 minutes. Like, it's a total of 2.5 miles. And then the last 15 minutes from 45 minutes to 60 minutes shows that she ran a total of 3 miles. So you'll notice that her rate is not linear. And the reason hers is not linear is because she's running up a mountain. She's getting more tired as she goes. It's not like this flat, constant speed. When you're running up a hill, it's harder and you're going to go slower. So the first 15 minutes she ran 1.5. Then she only ran about another half a mile. About another half a mile, right? So this first bit where she ran a lot faster than the rest of the time she ran. And the reason is that first chunk of time, she had just started. She wasn't as tired. And it says that she started on a flat, rocky trail. And then it became a steep mountain. Okay? So make sure you have this down. Make sure you understand why this top one is linear, why this bottom one is not linear. The top one has a constant rate. The bottom one does not have a constant rate, has a variable rate. Okay? Let's continue. All right, example number 2, it says, the rate of change of a function can provide useful information about the relationship between the two quantities. A linear function has a constant rate of change. A nonlinear function has a variable rate of change. So this is what a linear rate of change looks like on a graph when it is increasing. This is what a linear function looks like when it's decreasing. And this might be what it looks like in the graph. You could find a constant rate if we found m for any of these. It's going to be the same every time for every row. Okay? Off to the right, this is a nonlinear function. You can see that it's curved. Whether it's increasing, whether it's decreasing, sometimes it's just wobbly too. It's increasing and decreasing. And if we were to find the m or the slope within this table, it's not the same. Some of the rows are going to be different. Okay? So let's look off to the side at number 3. It says, different breeds of dogs have different growth rates. A large dog breed typically experiences a rapid growth rate from around birth to 6 months. At that point, the growth rate begins to slow down until the dog reaches full growth around 2 years of age. Sketch a graph that represents the weight of the dog from birth to 2 years of age. So it's not even telling us any amounts. It's just saying sketch a graph to represent this. So from birth to 6 months, it's going to have a rapid growth rate. So I'm going to show that by showing like a really steep increase. So from birth to 6 months, let's just say, okay, well, it goes from 0 pounds to 20 pounds maybe. So I want to go from 0 to 20. Pretty steep growth rate. Okay, then the weight begins to slow down until it reaches 2 years of age. So from there, I'm just going to slow my growth rate down and not make it go up as fast. Okay? Is the function represented by that graph linear? No, this is not linear. The rate of change is not constant. Meaning, the dog doesn't grow the same speed every single month. You can see that the graph is curved. Is the function increasing or decreasing? Well, it's increasing. You can see that the function is going up over time. Just because it's not going at the same rate, it is still increasing. Okay? The dog gains weight over time. All right? Make sure you have that down. On the next couple of slides, you're going to be doing this. You're going to be reading a couple of situations and then determining if they are linear or nonlinear based on the graph that you create. Okay, you can always reference this page that shows you what linear and nonlinear functions look like. Let's continue. All right, number 4, it says, Nika took her laptop to school and drained the battery while typing a research paper. When she returned home, she connected it to a power source and then, the battery was recharged at a constant rate. Sketch the graph that represents the battery charge with respect to time. So there's a couple things going on here. What I suggest you do is you highlight each thing that happens as it happens. So the first thing that happens is she took her laptop to school and drained the battery. Okay? The next thing she happened is she returned home, connected her laptop to a power source, and it recharged at a constant rate. And we want to graph this situation here on the graph. So let's say when she got to school, her computer was at 100%. Okay? And then she worked on it throughout the day. So maybe she worked on it in the first class she was in, and the second class, and the third class. And by this third class over here, her battery was drained. Okay? But it wasn't really being drained at a constant rate. So maybe the first hour she used a little bit of computer. Second hour she used a little bit more. So let's just say this is her rate of her using the computer at school. Okay? But it said that she drained it, so I want to make it go even further down. Let's say right here. She drained it. Okay? She got home and she plugged it into a power source. And so let's say this is her walking home. She doesn't plug it in, it doesn't change at all. And then once she plugged it in, it increased at this constant rate. So we have a straight line showing the constant rate of increase in the battery. Okay? Is this function linear or nonlinear? Definitely nonlinear. The constant, or there is no constant, rate of change throughout. Okay, there's a constant rate of change right here, but everywhere else there's no constant rate of change. And then it says, is it increasing or decreasing? Well, both. When her battery drains, the function is decreasing. When she plugs it in, it's increasing. Okay? Make sure you have this down. You're going to try one of these out on the next slide on your own. All right, I want you to give this a go. It says the long jump is a track and field event where an athlete leaps as far as possible from a given point. Mike Powell of the United States set the long jump world record of 8.95 meters, which is almost 30 feet, during the 1991 World Championships in Tokyo, Japan. Sketch a graph that represents the path of a high school athlete attempting to jump. Okay? So this is a little bit more difficult. The length of the jump is right here, and the height of the jump is right here. So think about someone jumping, okay? And I want you to graph what that would look like. So as they leap out, how far are they going up? And you're gonna, whatever, do a graph based on what you think a jump will look like. So really imagine a person in their arc as they jump, and then draw that arc on this graph and then answer these two questions. Is the function linear? And is it increasing or decreasing? Okay, and then we'll go over this pretty soon. All right, I'm going to show you what my graph would look like. Our graphs are probably not going to be the exact same, but they need a few of the same features. So before an athlete jumps, they're starting at 0, right? Now when I imagine someone jumping, as they jump out, they're jumping higher, right? So they're jumping out, they reach this peak, and then they fall back to the ground. So this is what my graph would look like, okay? Something like this. So as this person jumps out, they go up as well, right? Yours could be a little bit different than that, but it does need to have this same pattern of going up and then down. Is it linear or nonlinear? Nonlinear. Why? Not a constant rate of change. You can also say it's not straight. And then, is it increasing or decreasing? Both. It increases at first, right? And then once that jumper hits the peak, it decreases. Okay, so make sure you have that down before we move on. Let me know if you have any questions in the chat. All right, moving to exercise 2. It says Lamar and his sister are riding a Ferris wheel at the state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution. The graph represents Lamar and his sister's distance above the ground with respect to time. So you can see that they start pretty close to the ground. They go up, right, to the top, and then they go back down. And then they go back up again, and then they go back down, and then back up, etc., right? This is them on a Ferris wheel. And eventually they make it all the way back down, and they stop. So using this graph, answer these questions off to the right. Is the function linear? Where is the function increasing? What does that mean within this situation? And where is it decreasing? What does that mean within this situation? So go ahead and answer those questions, and then we'll go over them shortly. All right. Based on this graph, this is a non-linear graph. There's no constant rate. And the line is not straight. That's your reasoning. Okay? Where's the function increasing, and what does that mean? It increases each time the Ferris wheel goes up, right? And that's happening in quite a few different places. It's happening here 2, 3, 4, 5 times. Okay? And then it says, where is it decreasing? Well, it's decreasing each time it goes down. And that's happening here, 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 and here. Okay? Make sure you have that down. Let me know if you have any questions. All right, last exercise here. I want you to read through these 4 scenarios and then match them to these graphs below. So the first one. This graph is going to show the change in a smartphone battery charge as a person uses it more frequently. Okay? The next one, a child takes a ride on a swing. The next one, A savings account earns simple interest at a constant rate. And the last one, a baseball has been hit at a Little League game. Okay? So match these graphs, and you'll notice that these graphs don't have any numbers on them, but I want you to do your best. Okay? All right, the one that I started with here was number C, letter C. And the reason why I started there is because it literally told me that it had a constant rate. So I can see that this is a constant rate. So this is C for sure. The next one I did was D. So I thought about a baseball being hit. So it starts off kind of close to the ground. When it gets hit, it goes up into the air, kind of arcs down, and then falls completely to the ground. And that looks exactly like this situation here, in my opinion. So I said that one was D. That leaves A and B. So one of these is representing a smartphone battery as someone uses it more frequently. The other one's representing a child swinging back and forth on a swing. So I thought, you know what? If someone's swinging back and forth on a swing, there's a pattern, right? They're going up and down and up and down and up and down. And that is shown by this one right here, right? You go up and down as you swing on a swing. So this is scenario B. And then the last one I did was scenario A, right? Someone starts off, their phone's pretty charged, they're using it, and then they start using it like crazy, it drains the battery. So this is scenario A. Okay, let me know if you have any questions about this. Again, the answers are C, D, B, A. We're going to move into our closure and then get into our exit ticket. All right, just to summarize this lesson, the graph of a function can be used to describe the relationship between what it's representing. A linear function has a constant rate of change. A nonlinear function does not have a constant rate of change. If it's positive, it can be increasing. It's called increasing. If it's negative, it's called decreasing. And some functions may do both. They may increase and decrease as they go. Let's go over our exit ticket before you get into it. All right, here is your exit ticket for today. It's pretty similar to what we have done all class period. It says Lamar and his sister continue to ride the Ferris wheel. The graph below represents Lamar and his sister's distance above the ground with respect to time during the next 40 seconds of their ride. Name one interval where this function is increasing. So what I want you to do is I want you to find a time section. So maybe you'll say, okay, well, from 20 seconds to 40 seconds, from 60 seconds to 70 seconds. Just tell me where it is increasing. So it's going to say something like blank seconds to blank seconds. Okay? And you're going to do the same thing here except for decreasing. Tell me one place on this graph, one interval where it's increasing or decreasing. Then you're going to answer if it's linear or nonlinear and give me a reason. Then you're going to tell me what could be happening during the interval from 60 to 64 seconds. So that is represented right here on this graph. What could be going on there? Okay. And then it says, based on the graph, how many complete revolutions are made during this 40-second interval? So basically, how many times does it go up and down? Okay? And that's your exit ticket. When you finish, please do your lesson reflection in Google Classroom and then work on your weekly work until we go over this. Okay? Good luck.